Hi everyone, welcome to my channel. So this video is going to the last part of activation functions. So in this video we will discuss about swish and Maxout activation function. So let's see. So swish is also named as self-gated. So actually in the recent times, ReLU is being famous and it is being widely used for many of neural network architecture instead that we have already in like leaky ReLU and parametric ReLU, but ReLU outperforms all the related ReLU that we have already discovered. But for deeper neural networks, actually Swiss is quite better than ReLU, because actually if we are going to use some 40-50 layers, there actually in between the layers we can use Swiss for better results than ReLU. And Swiss is basically non-monotonic, which means it is not increase through a certain direction with increase in the weight, and it is bounded in the positive value and unbounded in the negative values as well. And as you can see, it is nothing but this formula. So the x here is a scalar value, so scalar into the sigmoid of any sigmoid of that particular s scalar. So yes, this is nothing but the ReLU that we have already seen. So ReLU, this is giving 0 for negative values and all positive value for the positive results. And it is nothing but swiss. This is the swiss function. So yes, it is non-monotonic. Yes. Okay. So as you can see, the advantage of it, supposedly it resolves the vanishing gradient problem, because as you can see for negative it is not giving 0, and the derivative also it has some values, positive values, so that we are avoiding vanishing gradient. And here actually we can see the value that if your input is some 100, actually reduced to 50 as we are using sigmoid activation function. And it is like it non-linearize the data set. So if you provide any linear values, supposedly if you provide any linear value, actually it turns into non-linearize the data, so we can understand the complex pattern in the data set. And it is also zero centric. Zero centric means it gives the derivative for both directions, so it is gonna uh, helpful for weight optimization while doing the gradient descent. Okay, so this is all about Swiss. And one more activation function is max out activation function. So it is nothing but it chooses the max of the input that goes to the activation function. So as we know, the activation, like the input for this is the input for the activation function that goes. So which is um, the weight, the multiplicative summation of all weights to the input with some bias. So actually it conducts all the input that goes to that particular activation function, and it chooses the maximum one. So this is nothing but the max out activation function. So yes, as you know, many activation function are saturated, means it is giving some saturated value 0 to 1, and so that the gradient also becomes saturated. Bec- but in here actually, cause this they have slope for some range, as they have slope from for some range, because if you choose sigmoid activation function, it has some 0 to 0.25 gradient or derivative, as you can see. But here actually we do not have that much saturated or range values. So it basically what it does, the max out activation function, it takes the pre-activation and converts the matrix containing uh, con- containing the maximum input. So what is the maximum input? So this is the maximum input, so it provides the matrix out form. So matrix out form means, so it conducts the weight and tries to multiply the matrix multiplication of uh, the input with some addition of some matrix bias. So yes, this is nothing but the Maxout activation function. So here actually we have finished all activation functions in this particular channel. So thank you guys, thanks for listening.